Right, now you've got your results, let's have a look at what you can do with them and how to find a value for the speed of sound. Here are my results. I've plotted a graph of frequency on the y-axis against volume on the x-axis. If you don't have graph paper, there are plenty of places to download it online, but you could just as easily do this on a spreadsheet, which I'm going to do in a moment. Now, you've got a curve here. Mathematically, there are lots of different relationships that will give a curve that looks similar to this. And it's very difficult to tell by looking what we've got. However, what we're looking at here, or rather what we're hearing, is something called Helmholtz resonance. And that's what determines the way that particles of a gas vibrate inside a container. And that's what makes the sound. And that relationship tells us that the frequency of the sound depends on 1 divided by the square root of the volume. Now, it looks a little bit messy. You could either go through with all your results now and calculate 1 divided by the square root of the volume, or you could put it onto a spreadsheet, which is what we're going to do. And then we're going to look for a graph like this with frequency against 1 divided by the square root of volume. And that should give us a straight line. And it's the gradient of that straight line that will allow us to calculate a value for the speed of sound. Okay, these are my results here. I've got volume in this first column, and then I took 3 readings of frequency just to check that they were quite consistent. And they are. If you look, most rows, the frequency values are exactly the same, or very, very slight differences between them. The only problem here was this row, where I've got 195, 196 and 207, so I suspect something might be not right there. If you're wondering why this row is blank, it's because I just could not get a sound at all at 650. I don't know why. So I'm going to go with this, and I'm going to try to draw a graph of frequency against volume. And just in case you don't know how to do this on a Google Doc, highlight the 2 columns you want. You click on Insert Chart, and Google will pop up with the graph here for you. Now, it's given me here a line graph, and I don't want a line graph. See here where it says line chart? I'm going to scroll down here and choose instead a scatter graph, and then it will plot the points for me instead. Now, it looks like we've got 1 point slightly out of place there. What's the chances that's this one here, where we had 195, 196 and 207. So I'm just going to see what happens if I change that to 207. Oh, look at that. Right, we'll stick with that, I think. Now, this actually isn't the graph we want. We've already seen that what we really want to plot is the frequency against 1 divided by the volume square rooted. So in this column here, I'm going to make an extra column to do 1 divided by the square root of the volume. Doesn't really matter what you call it. It's difficult to get the formatting right in these cells. But what's important is the formula and how we calculate it. So in here, I'm going to click in the cell where I want to do a calculation, and then I'm going up to this bar here, and I'm going to put equals 1 divided by. Now, to do the square root, I have to first open a bracket, and then I'm going to put SQR, there it is, square root. And I want the square root of this 150, so I'm just going to click that, close the bracket. There it is, it's calculated it for me. Okay, now you don't have to do that for every row, because if you click on that, and then see where that little blue square is on the corner, grab it, pull it down, there's your formula into all of those different rows. So that's the data we want to plot now. We want to plot this frequency against this square root, 1 over square root. The problem here is that Google Sheets won't manage this very well, because it only likes to draw scatter graphs if I'm using only the first 2 columns and no formulas. So to get around that, I'm going to go down to the bottom here and click to get a new sheet. And I'm going to copy the data I want into here. So I'm going to take this column 1 divided by the square root. I'm going to copy that, and I'm going to put paste special, and I want the values only. That's because I do not want the formulas copied into there or the graph won't work properly. And then I'm going to go back and copy the frequencies. There we go. Okay, so now we should be able to draw a graph of these, and this is what we're hoping is going to be a straight line graph. So I'm going to highlight those, insert chart. Now this time it has given us a scatter chart straight off. That looks like a reasonable straight line. If you had this on a piece of graph paper, you could probably quite easily draw a straight line through that. We can get the Google document to do that for us by clicking up here where it says Customize. So if you click on Customize and then choose Series here, then scroll down and click there, Trend Line, and it will give you a best fit straight line through there. And then if you scroll down a bit further to Label and say Use Equation, it will tell you the equation of that line, and that's really useful because that number there before the x is the equation, is the gradient of my graph, and that's what I'm going to need to calculate the speed of sound. So let's take note of that number and let's see how we use it.
Okay, so what we're going to do with our results? Well, first of all, let's have a look at the equation that actually describes Helmholtz resonance. Now, the full equation says this: the frequency depends on V. That V there is the speed of sound. V over 2 pi times by, now this is what makes it look ugly, times by the square root of A over L, and then the 1 over the square root of V, which we've already got on our graph. Now, it looks a bit of a mess at the moment, but we know that the V on the bottom under that square root is the volume. The A is the area at the top of the bottle, and that's why you need to measure the diameter of the top of the bottle. And the L is the length there that we measured as well. Okay, so what it means is this equation, now if you remember your maths, you will know that there's an equation that describes any straight line, which is something like this. And the thing that goes in front of the x is the gradient. That's the number we read from our graph on the previous page. And it was, so I don't forget it, I'm going to put it there, 3237. Now, this bit is our gradient, because that's what we plotted on the y-axis, that's what you plotted on the x-axis. So the bit that multiplies the bit on the x-axis is our gradient. So we know that our gradient equals this. We want to find a little v though. We want to find that speed of sound. So I'm just going to rearrange this into a form of v equals. So the gradient is going to have to be multiplied by 2 pi and then multiplied by that thing upside down. Yep. Okay, now how are we going to do this? The gradient we've got 2, we know, pi is 3.14, so it's the L over A that's the tricky bit. Now the L is straightforward enough. My L, I made that 8.5 centimetres. Now everything in this equation is meant to be in metres. So I'm going to turn that into metres, 0.85 metres. Now for the area, well, I measured my diameter and I got 2 centimetres. So that would be 0.02 metres. Now the area of a circle is pi times the radius squared. If the diameter is 2 centimetres, then the radius is 1 centimetre, or 0.01. So our area is pi, which is 3.14, times by 0.01 squared. Now on a calculator, that's probably going to give you as your answer 3.14 times 10 to the minus 4 but that just means 0.000314. Okay, so the next step is to put our L and our A together under that square root sign. So what you're going to have to do there is do your L, 0.085, divide it by your A, 3.14 times 10 to the minus 4, or if you prefer, 0.000314. And then when you get that answer, you're going to have to take the square root of it. And when I do that, I get 16.45. Now, there's one last thing we're going to have to do before we put all of this together, and that's to make an adjustment to our gradient, because everything in this equation is meant to be in meters. And my volume on my graph was measured in milliliters or centimeters cubed, not meters cubed. Yep. Now, there are 1 million centimeters cubed in a meter cubed. But we didn't use the volume, we used the square root of the volume. And the square root of a million is 1,000. So we need to adjust by a factor of 1,000. So I'm going to take my gradient and I'm going to divide it by 1,000. So that number that we read on the graph on the spreadsheet was 3237. So when I divide it by 1,000, it's going to give me 3.327. I'm going to round that to 3.2 because most of the measurements we took weren't to any more than 2 significant figures. It seems absurd to keep such a long number in there. So 3.2. So now, in this equation here, we're just going to put all the things we've got. So we've got 3.2 times 2 times pi is 3.14. And that thing there in the square root, we know came to 16.45. And that gives me, it's absurdly good, this. It's almost as though we'd been cheating. This gives me actually 331 meters per second for the speed of sound. Now, if you're not sure what the speed of sound is meant to be, go and have a Google. That is a pretty good answer.